For millennia, warfare meant mass, momentum, and explosive force. Today, the front lines of global conflict are completely silent. The human brain processes information at a fixed biological speed, but modern defense networks are flooded with millions of data points every second. Human decision-making is struggling to keep pace with the raw volume of incoming data. Because of this, nations are racing to achieve what strategists call tech sovereignty, the ability to secure complete independence over their own computational infrastructure and hardware. In this environment, strategic advantage shifts toward the side that can outcalculate its opponent across millions of variables at once. You can see the physical scale of this effort in the layout of these research campuses. This infrastructure provides the foundation for the next generation of strategic modeling. Inside the Lawrence Livermore National Laboratory, researchers operate an exascale supercomputer known as El Capitan. It processes over a quintillion calculations per second. This visualization shows the mathematical physics of a weapon's core. Scientists use these high-fidelity simulations to test and iterate nuclear stockpile designs entirely in a virtual environment. These massive datasets are then fed directly into machine learning systems. The AI autonomously identifies the most efficient structural architecture for a weapon, long before a physical component is manufactured. Decades of trial and error are now compressed into trillions of calculations performed every second. These theoretical designs are moving from the laboratory to active theaters of conflict. This data shows the rising frequency and expanding geographic reach of intermediate drone strikes. According to the Institute for the Study of War, these campaigns have become a constant presence on the modern front line. This is the physical reality of that data. An autonomous system navigating through cloud cover to monitor contested territory below. The U.S. Department of War is working to integrate AI processing directly into these flight operations, allowing the systems to analyze targets in real time. By delegating tactical decisions to an algorithm, a military can maintain a persistent presence across thousands of miles of territory with a minimal human footprint. This pushes us into what defense experts call cognitive warfare, a stage where cyber, space, and physical operations are controlled through a single unified data stream. This network diagram shows how algorithms initially functioned as passive tools, gathering inputs from satellites and sensors into a central logic node to generate logistical predictions for human commanders. The software becomes an active combat driver once granted authority to identify and lock onto targets without waiting for a human signature. At the highest escalation, a single algorithm can coordinate dozens of drones into a synchronized swarm, executing complex maneuvers without external intervention. In this new environment, the lethality of the system is determined by the speed and precision of the software guiding it. Software evolves at the speed of computation, while the frameworks meant to govern it move at the pace of international diplomacy. This has created an intense focus on the United Nations in Geneva, the traditional hub for global disarmament negotiations. However, current international treaties were written for physical hardware like tanks and missiles. As the German Marshall Fund notes, this leaves a massive regulatory vacuum for digital warfare. The UN Institute for Disarmament Research is now attempting to establish governance benchmarks for lethal autonomous weapon systems, or laws, to prevent an unmanaged escalation. Without these benchmarks, the speed of automated systems creates a risk of conflict that escalates faster than any human diplomat can intervene. This comparison shows the difference between tracking physical warheads and monitoring code that copies infinitely without detection. Digital weapons duplicate and transmit across a network in milliseconds. This makes traditional arms control inspections, which rely on verifying physical sites, far less effective. The international community is now forced to define entirely new frameworks for cyber stability that account for the unique nature of replicable code. The challenge is maintaining oversight of systems that adjust their logic at speeds far beyond the capacity of human observers to verify in real time. The fundamental 21st century challenge is defining the terms of a peace treaty for an algorithm.